such an approach that resembled a graphics problem. So it was like, doing this rather than, it was not the natural way of scratching yourself, So it was great, and a lot of enthusiasts took advantage of that. And there were some very attractive features. You could handle large data arrays, and it had this idea of streaming throughput. It was massively parallel, single instruction, multiple data. It was low latency floating point computations, like, for instance, computing distances or 1 over a distance. This is something that in graphics is done a lot. Rotations, they were like, the hardware support was tremendously appropriate for that. The floating point operation precision was IEEE 754 compliant with some exceptions, and I'm not going to talk about that. But again, it was relying on the library API, and it was not a pretty thing. And as I said here, mapping computation problems to graphics rendering pipeline was not for the light-hearted. It was not straightforward. And this is where CUDA came into play. CUDA is just it's a collection of, it's an API to a library that basically opens up the access to the hardware for the average Joe. Okay, you don't have to bend backwards to fit your problem to look like the graphics pipeline. You can just basically take your data, copy it down there, execute the kernel, and bring back the useful results. And it was targeted for the scientific computing community, and it had a standalone driver. You can very easily invoke a GPU computation. The interface was designed for compute, so it was not. It was a graphics-free API. It had guaranteed the maximum download and readback speeds, and you could handle, manage to a very large extent the memory available on the GPU. So I told you a couple of things about the hardware. I told you a couple of things about how people used the hardware in the past and about this CUDA programming model. And now I'm going to talk a little bit about the specifics of CUDA programming, okay? To give you an idea about how things get done using CUDA. The basic idea here is that the GPU is used as a helper, and the CPU runs jobs, and at some point it farms out a certain chunk of computation to the GPU, which minds its business and does the computation, and then when it's done, it just silently sits there for the CPU to bring back the data that was generated on the GPU. So this is the model. In general, the CPU is busy with computing, these corner cases, like if then else, doing all sorts of bizarre computations that are not parallel in nature. Because what you can do on the GPU is a fairly small set of tasks that are very parallel in nature. So it's not the typical if then else, heterogeneous type of, divergent computational paths. No, it's just like the same instruction executed by 240 cores at the same time. Okay, so it's just like, for instance, if you want to paint the same painting 240 times, you just have 240 canvas, and the first core does this, and then the second one, they all do this, and then they draw a line like that, and then at the end, you see a face, all of them finish the same time and such. So that's the idea. For that is good, but not for if then else and such, where threads divergence and for that type of computation, the CPU deals with these corner tasks. When you do GPU computing, you have to pass data down into the GPU. Then you have to fetch back the results. So there is an overhead associated with that. And I showed you on a slide there that the rate, the communication rate, is something like 8 gigabytes per second, which is not bad, but is not good either. So in order for you to use GPU computing, you better have a big job that needs to be done in parallel. Otherwise, it will be overshadowed by the amount of overhead that is associated with pushing down data and then recovering the results. So this is one thing that you need to keep in mind. A little bit of nomenclature here. If you start reading about CUDA, you see that they start talking about device and host and kernel and such. So host is the CPU, device is the GPU. And the computational model is the device invokes, the host invokes the device by launching a kernel. The way you should think about a kernel is like think of a short function, not necessarily short, but typically they're not that convoluted. A pretty straightforward C subroutine that gets executed identically by thousands of threads. That's a kernel. And when it is launched, the device is told on how many threads it needs to execute that kernel. So in other words, you want to do a set of tasks like drawing that painting, face of a person. Then how many paintings do you want to draw? 10,000, 1,000, whatever. And because what happens is that the GPU will start drawing that painting as many times as you want. And that's, you tell how many threads that kernel needs to be executed on by specifying an execution configuration. And just to put things in perspective, this is how you do that. When you have a kernel that needs to be executed, you specified how many blocks you want to have it run on, and in each block, how many threads you have in that block. There's a limit on the number of threads that a block can hold, namely 512. So if you want to draw 100,000 paintings, and given that you can have at the most 512 threads in one block, you have to have 20,000 blocks, something like that, but a large number of blocks, right? So this is how you tell the device, the GPU, how many threads will end up executing the kernel. There are some limitations here. Before I get into those limitations, let me point out one thing here. By default, the execution of the host doesn't wait for the kernel to finish. So the execution is asynchronous. So what happens is that the host executes instructions, and at some point it launches the kernel, but it does not wait for the kernel to finish, and it continues to execute instructions. And at some point, it makes a call to copy stuff from the GPU, right? Now, there are two scenarios there. The GPU finished, and therefore immediately, it can copy back, or the GPU did not finish, at which point the host waits on the device. But it's asynchronous. If it launches, it can continue to do other things, and the GPU runs here, and the CPU runs here, which is nice. An example here of running a kernel called foo, and you say, I want to run the kernel foo on using 100 blocks, and each block has 256 threads. So effectively, it means that whatever subroutine foo is, that kernel, it will get past these two pointers, and it will get that subroutine will get executed 25,600 times. Okay, and now an important thing: usually these pointers are pointers to memory on the GPU, right? So that's important because you cannot access data from the GPU onto the host. Okay, GPU sees only the GPU universe. If you go back a couple, if you remember what we presented about what we discussed about a couple of slides back, I told you about this idea of stream multiprocessor, and I told you that each stream multiprocessor has 8 scalar processors. And the reason why that concept of stream multiprocessor is important